pretty amazing putting all this together, and it's not just here. He's doing this all over the country, working with Joshua and the team that puts this together is, really cutting edge stuff to bring this kind of education. So I'm going to be the science guy for the next hour and a half, just talking about basic soil. What's going on. I'm a professional horticulturist for 47 years, so I've had my hands in soil since I was 22. Field grown, container grown, ornamental horticulture. So soil is really the foundation of everything that we're doing, and we sometimes tend to lose sight of that, exactly what's going on down there. And as we get a greater awareness of what's actually working down there and how that's happening, it leads us into good management decisions, and we can take sort of best management practices. So we know, most of you have been growing the cannabis plant for many, many years and have a great understanding of that plant, what it takes to grow that plant, to grow a quality plant. Now we're at a point we're going to try to look at what's actually happening in the soil to make that happen. I title this a systems approach, and that's really what it is. We don't focus strictly on the plant. We don't focus strictly on the inputs. If we were growing conventionally, we'd be in a product-centric program. So conventional practices, and you're looking at somebody that spent 20 years as a conventional grower. I cut my teeth in the early 1970s when I was taught by university and cooperative extension that I couldn't grow any horticultural plant without a reliance on synthetic fertilizers and chemical pesticides. And I used it all, and I used it all for a long time. Until the mid-1990s, I realized I was on this treadmill because synthetic pesticides don't grow any plant on the planet. Pesticides only treat symptoms. They don't ever solve a problem. So depending upon the plant that you're trying to grow, if something manifests itself in the plant, in the soil, if it's a weed, it's a fungal disease, if you have an insect pressure, it is the symptom. They aren't the problem. And typically we say, I have a problem, I have an insect infestation, I've got a fungus disease moving in. And we tend to zero in on that as a problem that we have to try to solve, when really that's only a symptom that's telling us that something's out of balance in this whole system. So a systems approach to management, and my perspective now and for the last 22 years is 100% organic. So I work in agriculture, I work in land management, high profile. I do professional baseball fields, high profile soccer fields. All the same, there's correlation between all of that. And it's really about trying to meet the expectations that we have. So all of you as growers have an expectation of what you want to produce. You have an expectation of what that crop wants to be. The same thing with that NCAA soccer field. There's an expectation on what that is supposed to be. So now we are learning our management strategies designed specifically to meet expectations that we've set for ourselves. And growing organically, growing regeneratively, leaving soils better than we found it, closing those loops, bringing that all together, and looking at it all as a system. So the way I look at it, my system involves the microbes in the soil. I'll touch a little bit about that. I know Leighton's going to go into that in more detail later on today. So we have the soil and the microbes and all of its function. We really have to rely, when we need to make an input, we have to rely on the exclusive use of natural organic input. So in other words, in my programs, I don't have much of a tolerance for synthetic inputs or fertility because think about it, N, P, and K are just salt, mineral salts, and we tend to lose sight of that nitrogen, phosphorus, and potassium is salt. The more we introduce salt that comes in origins from a laboratory, the more destructive we are to this system and the harder it's going to be to meet the expectations that we have for that finished product. So we have the soil, the exclusive use of natural organic input, and then the cultural strategies that we employ. Leighton touched on, soils, compacted soils versus soils that are aerated or contain ample oxygen. And I'll weave in and around that a little bit. But those cultural things that we do. If we irrigate, how do we irrigate? If we're on natural rainfall, then we have those ups and downs and those periods that we can't control. All of those cultural things that we do then become married to the soil, the biology, and the natural inputs, and that's what creates the system for us. This isn't working. I don't know if that was exclusive to that one. Conventional view of soil. So this is these couple slides were given to me by Penn State. Penn State was a leader in how we looked at soils and how we looked at how everything related. And I'll touch on all these individual areas, but we have soil structure. That is also known as soil texture or particle size analysis, gradation analysis, and that is the sand, silt, and clay portion of the soil. The chemical, that is soil chemistry. So that is the pH, the relative acidity or alkalinity of a soil. The macronutrients, the micronutrients, something called cation exchange. How does that soil hold on to and retain nutrients? So all of that falls into soil chemistry. And then soil biological life. The conventional industry focuses on soil chemistry alone. They acknowledge in a passing way that there is something biologically happening in the soil, but nothing in a conventional program focuses on biology, so it's bypassing it. So when you're dealing with conventional inputs, think about just feeding the plant. You're taking something from a synthetic bag and it's going directly into that plant as soon as it comes in contact with soil moisture, and the whole biological system is bypassed, and you're actually degrading it to a point because you end up having, oh, is that what that was? I pulled that out, put that back. Thanks. Perfect. So we have that, we're bypassing that. So conventionally, this is how we've been taught to look at soils. Naturally, now an emerging view of soil health as proposed by Penn State back in 2004 or 5 says that no, these are all integrated. In order to grow anything in a healthy crop, we have to have an integration. So we learn how these interact. We optimize each area as much as possible so that those of you that, if we are container growing, and I've worked back in the East Coast developing soils for container cannabis production, and there's a whole lot that goes into that to develop that soil to get something that's porous, something that will grow the plant and give the nutrients that we need, and trying to build it all into that pot. If we're field growing, we're not going to change soil structure. If we have a clay soil, we have a clay soil. If we have a sandy soil, we have a sandy soil. So we have to learn to work with the soil that we have and not ever get caught in a trap of trying to change a soil to match something else if it's in field production. We have to have a strong focus on humus and that organic matter fraction. And I'll talk about organic matter and that fraction of the soil and how organic matter is the home for the microbiology. That's where it gets its support. Humus, as the end product of decomposition, is carbon and critically important, and you look at that as the driver of the whole system. And the humus fraction of soil is tiny. It can be less than 1% of the organic matter fraction, which can be 3, 5, 7%. So humus, very small fraction. Here we have disturbed and undisturbed soils. So on the left is a typical non-forest soil profile on average for North America, where we have 45% of that handful of soil as the mineral component, sand, silt, and clay. 5% of that on average is the organic matter fraction, and that's really the focus of where we pay most of our attention. The other two fractions at roughly 25% each are air and water, moisture to support the plant. So when you pick up a handful of soil, you look at that, it basically is half solid material and half pockets of air. Some of those pockets of air are filled with moisture, and the amount of moisture that a soil can hold is called field capacity, and that's a direct relation of the sand or the clay fractions. So that's really what you want to look at, is you pick up that soil and you want oxygen in there. You have to have that air fraction. On the right is a compacted soil. And you can see what happens. Compaction is not, we tend to think of compaction as heavy foot traffic or tractor traffic, equipment traffic, but rainfall, irrigation, the density of soils is called the bulk density. Bulk density is the weight of a soil per cubic yard. There's a bulk density fraction and a weight. That weight is directly related to how much solid material and how much pockets of air are contained in there. When we have this compacted soil, you can see the fraction here, how the mineral portion becomes by far the largest portion of that handful of soil. And look where the organic matter fraction shrinks down to, all the way down to, it could be down as low as 2%. That's the home for the microbes. So as that organic matter fraction shrinks, the ability of those microbes to proliferate and do those things that Leighton was telling us about gets dramatically reduced. And then the soil can hold less oxygen, and therefore it holds less water. So what we always are striving for is that pie chart on the left, and we can test this. We can out-test bulk densities of soil. We can get a penetrometer. We don't even need a penetrometer. You can take a screwdriver and just go out to a soil, and you should easily be able to go down in there. And if you can probe at random spots through a field and easily get down in, then the assumption would be that you have enough pore space down there to hold on to oxygen. So components of soil. Soil is made up of minerals from parent rock material. That's the sand, silt, and clay, and that varies in all regions of the country. We have organic matter, moisture, gas, air, the microbes themselves, and then plants and plant roots, and the decomposition that happens in the root of plants. All plants slough off root systems constantly, and the microbes break them down, and that's passively over time building an organic matter fraction. So all of these would be considered to be components of soil. So soil texture, as the first one, it's a function of these relative portions of sand, silt, and clay. They can contain mineral nutrients. Soil texture affects nutrient and water retention, indicates a tendency of the soil to become compacted. Texture can be determined in the field with a ribbon test. So we send out to a laboratory. Every project I get involved in around the country, no matter what it is, I don't get involved unless they agree to test soils. And I test for soil texture, I test for soil chemistry, and I test for soil biological life. A ribbon test out in the field is actually pretty accurate. You just take a little bit of soil and you moisten it, and you roll it between your thumb and fingers, and you form a ball, and that ball is called a cast. If you can't even get it into a cast before it crumbles, that means your sand percentage is up in the 70% sand range or higher, because it just crumbles in your fingers. Now you take that cast and you roll it between your thumb and forefinger. And you're just like when you're little kids and somebody gave you some modeling clay and you decided to make little clay worms out of it. Ribboning it out, that's what it's actually called, is you're pushing it out and making it into a ribbon. The further out you can get that, the higher the clay percentage is, because clay is what imparts stickiness to soil. So if we can ribbon it out, 1.5 inches, then our assumption is that clay is up probably around the 10% range. The further you can get it out, the thinner you can make that ribbon, the higher the clay percentage. So understanding texture and what you actually have for sand, silt, and clay is critical to a good decision-making practice, a good decision-making strategy on how you're going to manage that soil. If we were going to engineer a soil to be the ideal soil to grow most plants, meaning engineering means taking raw materials and creating a soil, your target would be 65% sand. Somewhere around 5 to maybe 8% clay for nutrient retention, and the balance would be silt. And so that is generally accepted to be a target of an ideal engineered soil that has characteristics of nutrient retention and good drainage at the same time. Yes?
Where would you classify volcanic soil in that range? Is that volcanic work?
Yeah, I work on Maui with volcanic soils. So volcanic soils would probably be, for me over there, they probably fall right about in the middle of the spectrum, where, where they exhibit, we get good drainage most of the time. They actually are pretty rich in nutrients, depending on the age and all of that. But we would, and this is not in cannabis production, but managing soccer fields on the islands, and we're heading over there in a couple of weeks to do 4 islands. It's all volcanic soil, rich, but right about in the middle of the spectrum. Yes. Yeah, so field capacity technically means that you have a soil that has some arrangement of solid particles and air spaces. Heavy rain event, or you irrigate, all those air spaces, all those pockets fill up with moisture, and then through the natural percolation rate of that soil, all the freestanding water drains away. The moisture that is left is field capacity, meaning the appropriate moisture. So that's what I would want to do. I would want it to be moist or wet, let it drain away, get all the freestanding water out of there, and then do my test for probing. Because if I had a soil that was relatively high in clay and it was really dry, it's going to be very different than if it had moisture to it. You're going to get that real dry cakiness to it with the heavy clay. Yeah, and I do. I mean, I manage soils that are 30% clay, and trying to grow in it. So it's a lot of challenges. There's a lot of benefits if you have good clay, if you have clay soil with relatively high organic matter. Nutrient retention is crazy. It's off the charts. I mean, I'm working with CECs. We'll talk about that in a minute. Of 48 milli equivalents, 100 grams, and average is 12 to 15. That's my measure of nutrient retention. That means that if I'm working in an actively functioning biological system where that soil, that the biology is producing nutrients and cycling them there, I'm holding on to so much, especially ammonium nitrogen, NH4+, because NH4+ is attracted and held on to the soils very strongly. That means I have completely broken a dependence on a fertilizer bag very, very quickly. And that's the goal of all of this, is that we're trying to show that if you follow the strategies and the stuff that Leighton's going to take you through and others are going to take you through over the next couple of days, is that doing this, going out and buying fertilizer should be a thing of the past. And it's much easier to do in field production, but we're doing it on soccer fields and baseball stadiums and all of that. We're trying to get them half the fertilizer that they were using in a conventional program, and that they don't believe it. And of course they say, well, how can you do this? We're spending all this money and buying all this nitrogen. We're going to talk in a little bit about how nitrogen is critical to plant growth. We all know that. We'll go through what exactly is happening, but we don't have to have a dependence upon purchased nitrogen. And the whole idea of this is to get all of you to become more profitable. Less input, less out-of-pocket cost, greater yield, greater profits, better all across the board. And that's what we're happening, because as soon as we have a dependence upon supplied material product going in there, we're better off to just pick out something to feed the microbes and not even worry that much about feeding the plant and pushing all the N and the P and the K in there. And, I have presentations that I do that say beyond NPK, that we have to really think. And, think about, when you think about the whole synthetic side of the industry and nitrogen, phosphorus, and potassium, think about, think about the local parks that you see, or somebody's lawn or something, the expectation that's been created in our society, what that's supposed to look like. It's supposed to be this monoculture of a non-native plant that everybody's eyes pop out, and it's like that. And you think about that expectation, and where did that expectation come from? It came from an industry in 1950 that wanted to sell us product that was developed post-World War II. And then they came along with synthetic pesticides, and they said, all of that stuff, well, we're going to blow that out of there because that clover that was in there, that legume that's fixing nitrogen, that's not a good guy, it's a bad guy. So we're going to blow it out of there with an herbicide. Oh, and it just so happens we've got bags of nitrogen that we're producing in a laboratory we're happy to sell you because you're going to lose all the nitrogen when you kill the legume. And industry created all of that expectation to get us into purchasing product. So here we are all these years later, and it's time that we broke out of that mold and really took back. I mean, I have slides that say my best understanding of the highest managed landscape I do is simply mimicking a natural ecosystem. Because why do I think, or why does anybody in science think they have it better figured out than nature, nature itself does? So anyway, so soil texture, here's the USDA textural triangle. An ideal soil would be considered right down there in the lower middle, the one that's called loam. Loam, and these are all based on individual percentages of sand, silt, and clay and how they relate to each other. So when you have a clay soil, like some of the spots up here, you're up in the, you're working up towards the middle of that triangle. Where I'm from, I'm coastal Massachusetts. My soils are way down on that left-hand corner down there, sandy loams into loamy sands. I'm going down to work later this week in Malibu and Southern California, and I'm going to go on the opposite side of the triangle. So every different region of the country has its own. So you simply take the individual, you get a USDA textural, or you get a textural test analysis that comes back from a laboratory for about $25, $30, and you get a percentage of sand, silt, and clay, and just put it on this triangle, and you draw the intersect, and where the three lines intersect, that's your textural classification. So here is the size of all of these things. Gravel is anything larger than a grain of sand, and then silt, and then clay. So what this is telling us is that clay is microscopic. You have to have a microscope. It's a flat sheet. Clay stacks on flat sheets on top of each other. That's why it compacts. Think of a grain of sand, and it bumps up against each other. They don't compact unless people say all the time, well, sand can't compact, but it can if it's really fine sand, because sand can be subdivided into 5 other classes: very fine, fine, medium, coarse, and very coarse. But when you get these high clay soils, they're in sheets, and the sheets stack and stack and stack, and then that's where the compaction is, because you don't have those sand particles to break that up and to get the oxygen in there. Cation exchange capacity, very important concept. This is nutrient retention, and this is at the heart. This is actually the most important number that you could figure out for your soil, and this comes on a soil chemistry test, $25. Leighton talked about electricity in soils and electrical charges and all of that, and that's exactly what is happening. So in the well-aged humus portion of the soil, that small fraction of organic matter, and in the clays that you have here, now not all clays, there's kaolinic clay, more like clay, different clays in different region of the country, but generally speaking, clays carry a negative electrical charge. Humus carries a negative electrical charge. So what those do, those in the soil, they're referred to as CEC sites, or cation exchange sites. So what that means is that negative electrical charge will attract and hold on to cations. So we know that a cation is a positive charge. These sites in the soil are a negative charge, and what happens to electrical charges? Opposites, attract, like charges repel. So those positive charges, that's calcium, magnesium, potassium, ammonium nitrogen, that's a big one, NH4+. All of those are attracted to those exchange sites. If you're in a region of the country, probably more down south, I've done a lot of testing from here right up through Oregon, and very little sodium in your soils here. There's a little bit, but not terrible. Down south of Los Angeles, I have 14% of these electrical sites, these cation exchange sites, attracting sodium, which does me no good. And I have to get rid of the sodium, and there's a whole process to move the sodium out of there, and typically that's something that's done with a calcium source, like a gypsum, because sodium has a single plus charge, Na+. Calcium is Ca double plus. So that means it's more strongly attracted. If you have a low pH, which is on soil, a low pH means that you have a lot of hydrogen attracted to these exchange sites. because hydrogen is a cation and a positive charge. So now what do? Well, we know we have to raise the pH. We use lime, right? That lime raises pH because lime contains calcium or magnesium more strongly attracted than the hydrogen. So the calcium or magnesium is attracted to those exchange sites that needs to make room for itself. Hydrogen gets pushed off. So now what's the fate of the hydrogen? 2 hydrogen combined with 1 oxygen. Water. So you're displacing hydrogen with calcium and producing water that moves through soil solution. So CEC is affected by the soil type. They have this, and on these soil tests, you'll find over in a box, usually on the right-hand side, there's something called base saturation. Base saturation tells me how much calcium, how much magnesium is all attracted to these sites, and potassium. And typically speaking, in a productive agricultural soil science says that 2 to 7% of the sites would like to have potassium on there. Really important. Potassium is stress resistance for the plant. Any kind of a stress, weather stress, disease pressure, it's protection against disease. Somewhere around 10 to 15% of the soil wants to be magnesium, and anywhere between 50 and 80% of the exchange sites want to have calcium on there, and that would be considered to be a balanced soil. More sites in humus than clay, so that working with that organic matter fraction is critically important. Organic matter has a higher CEC than clay higher than silt, and silt higher than sand. So that's how we look at that. Now when we get the textural analysis, you put that together with soil chemistry, now you're starting to see how this all comes in balance. And then these are just tables of cations and anions. So you look over on the right, and because you probably notice I haven't mentioned phosphorus or phosphate, because phosphate is an anion, so it's not attracted to the exchange site. It's not held on those sites. It is attracted to positive charged sand particles. Phosphorus does not leach out of soils. You know, there's an interesting research. You know, we hear about phosphorus pollution, and of waterways and how restricting phosphorus. A lot of states have phosphorus laws, fertilizer laws that restrict it unless you have a soil test that shows you need it. Ag is exempted from that, but regular land management is not. So they did a study, and this is an interesting one. They did 3 test plots, and this happened to be with turf grass. One was fertilized organically. One was fertilized synthetically, both having phosphorus in them. One was the control and had no fertilizer at all. Turf grass. Which one do you think created the greatest phosphorus pollution and runoff? The unfertilized plot. Because phosphorus moves with wind and water erosion of soil particles. So now with no fertilizer, that grass thinned itself out because nitrogen helps keep it thick, and you had more bare spots, more exposed, wind and water, moved that off the site and contributed to the greatest pollution. So it really doesn't have anything to do with synthetic or organic fertilizers. It's how that phosphorus binds to soil particles. This is how plants mine for soils. The plant is going to tell the exchange site what it needs. The exchange site doesn't tell the plant. So in most plants, calcium is mobile in the root system. There's calcium above ground in the plant and calcium down in the root system, and it's not interchangeable. It stays up there and it stays down there. So if a plant needs potassium, and it's on that exchange site, and we've got potassium being held in that soil. So think of this, you have these exchange sites over here, even though they're all through the soil, but they're over here, and you have the root of the plant over here, and then in the middle you have what's called soil solution. So the calcium becomes an exudate from one of the root hairs or several of the root hairs of that plant, and that plant pushes calcium out into soil solution. Remember, calcium is very strongly attracted here, and it goes on and knocks off potassium because that's what the root wants, and it pulls the potassium back into the plant. So that's how, as long as we have enough nutrient in reserve, so think of exchange sites as a reservoir of nutrient, as long as we have that and we have that ability, the higher the sand percentage, the lower the reserve of nutrient we have, the lower that reservoir is. So the plant is doing the mining. So here's just cation exchange. This is what sheets of clay look like. So this is those, this is appropriate for the heavy clay soils up here. And that's what's happening. You can see why the exchange sites are so significant here, because both sides of those sheets are electrically charged, and then they stack on each other. So that's how they pull in and hold on to those nutrients. So pH, critically important. So we know the pH for the plants we're growing. We know the desirable pH for the cannabis plant. Every plant on the planet will take in nutrients at the maximum ability it can, depending on soil pH. So what we're trying to do is, without soil biology, pH is the whole sole governing factor on how nutrient gets into the plant. But we're adding the soil biology piece in there and creating that nutrient. So we're going one step beyond, soil chemistry, or way beyond soil chemistry, and we're trying to build that in. But this is the measure of given acidity or alkalinity of a soil. pH is affected by the organic matter fraction, by sand, silt, and clay, the soil texture, presence and numbers of microbes, presence and amount of cations and anions, and the presence of anaerobic conditions, low oxygen, no oxygen. We'll talk about that a little bit later. Here's a chart that shows the acidity and the availability of nutrients to most plants. So now we simply take the desired range for the plant that we're trying to grow, and we find it up there. And, I think with our production here, we're talking about slightly acidic soil is where we're sort of in that wheelhouse in the, mid sixes. And many plants fall into that. But if we're in that range, then all of those nutrients are readily available. So we know that phosphorus is important, in the flowering cycle of the cannabis plant. So nitrogen, is important up on the front side. Phosphorus kicks in. So look what happens if we allow our soils to drop down into pHs of 5.5, to 6. Phosphorus is there, it's present, and no matter how much is there and no matter how much we put in, the plant simply can't take it. So this becomes the very first step, and this can be done for $20 soil test and very short money to get pH. Now, one of the things is once we get the biological life in place, chemistry usually snaps in and follows that in. So if we were relying on a conventional program and bypassing the biological fraction, then we'd strictly be buying product to change the pH. But as long as we are working, think of a bacteria. A bacteria is pH neutral at 7.0. So if we get the right amount of bacteria working in there, we're going to buffer those soils. And even in acidic soil, in those regions of the country that run acid soils, the pH will buffer and you never purchase product again. It's the repeated use of synthetic fertilizers in acidic soils that drives pHs down. An example of what happens with this is, most of you probably know the plant, the hydrangea, blue hydrangea, and it's nice, deep, dark blue. Well, that's an acid-loving plant. And it is acid soil that keeps that hydrangea blue. And you use sulfur to keep that down. As pH goes down low, aluminum becomes very soluble in soils. Aluminum is what blues the hydrangea. That's why you drop the pH down with an acid thing. It used to be aluminum sulfate in a conventional program. It's elemental sulfur in an organic program. And you drop the pH down, aluminum is soluble, the hydrangea is blue. Now, if you systematically add calcium or magnesium in the form of lime and raise that pH, that blue hydrangea, even though it was bred to be blue, is going to turn lavender, and then white, and then pink. Because as you move up in pH, you're locking up that aluminum. It's no longer available to the plant to keep it blue, and you've actually changed the color of that plant. Because the nutrients that you need, to do that can't be there. So for the cannabis plant, we know the target pH range, so it's important that we work and to keep that there. pH adjustment, We do it when the pH is outside of the desired range, or when an extreme pH affects soil structure and soil health, which it can. The ideal time to use lime and raise the pH is during the cooler months of the year, and the ideal time to use sulfur to lower the pH is during the warmer months of the year. Typically, you're not lowering pH up here. We are down south. I've got soils in Southern California, 8.0 pH, and that's crazy high. And so, but sulfur, you need active bacteria, because active bacteria convert sulfur to elemental sulfur to sulfate through sulfuric acid, and then that lowers the pH. Liming, if we have to lime soils, we know we can't put more than 50 pounds, 1,000 square feet. That's a maximum rate for dolomitic or calcitic. Dolomitic lime is high in magnesium. Calcitic lime is high in calcium. Typically, most soil tests nowadays, we prefer calcitic lime because of just the obvious things that we just talked about with calcium, and we talked about how that works and replaces the hydrogen. Elemental sulfur, as I said, needs to be converted by the microbial fraction. It is an anion. It is leachable. It's not held onto in the soil, but you need warm, moist, and well-drained soils for this to be functioning, because all of those things are conducive to healthy microbial populations. Water movement, clay versus sand, a big deal when you're working in a clay-based soil. Water moves differently, as we know. Clay, fine textured, sand is coarse textured. Water movement influences root development and depth. Roots are going to follow water as it moves down. So if water doesn't percolate and it's always sitting up in the top part of that soil for an extended period of time, the root system is going to stay there, and the root system is going to suffer. Water movement can influence compaction. When water sits too long up near the surface, we get a compaction layer between that water and what's happening down below it. And probably the biggest thing is excess water, meaning slow to drain, creates an anaerobic soil environment, no oxygen, because water is replacing all the oxygen that should be in those pore spaces that surround all soil particles, and then the end result of that is either going to be a fungal disease of the root system, or possibly ultimately the serious decline of the plant. I'll talk in a little bit about what actually happens down there. So deeper roots improve the soil. So on the left, you have managed turf grass. There's your park, there's your lawn, and then you move through. We all know the root system that can be produced by the cannabis plant, and that's really what we're trying to do, is to drive the root system and to get it down and do as much as that can do. This is a ryegrass as a grain, and look at main root, secondary, tertiary, and quaternary roots. A total root mass, 380 miles. One plant, grown as a grain in a healthy, biologically active soil that exhibits the characteristics that we've just talked, the desirable characteristics that we've just talked about. Soil organic matter, the most important thing, if there's no other takeaway from my time up here, is the importance of the organic matter fraction. Organic matter is the driver of the system. 3% organic matter is considered to be the low line for successful horticultural growth. I manage soils right here in California down south at 1.6% organic matter. Ridiculous. I have a baseball stadium that I do is 96.8% sand. Organic matter fraction is 0.9. So that means I don't have much going on. So as you improve the organic matter fraction, we can do that depending on where we are. We test and see where we are. The introduction of a biologically active compost, and Leighton talked about that. I don't think I have a compost slide in here, but all I can say, and I know you're going to expand on this, right, Leighton? Compost. All compost is not created equal. And I've seen stuff that you look at, it smells good, it feels good, it's great, and then you put it under a microscope or you run soil chemistry tests and there's nothing there. So compost should do three things for you. It should give you organic matter, by definition, 35 to 50% organic matter. It should give you ample biological life. with both the lower trophic level organisms, bacteria and fungi, and then the higher level predators of the protozoans, the flagellates and the amoeba. They move in after a composting process happens. They're not active in producing in the actual breakdown. It's bacteria and fungi that make that happen, mostly bacteria, but protozoans move in at the end, and you want that big population. And then there should be nutrient. You should have anywhere between 0.9 and 1.8% nitrogen, 0.5% phosphorus, and 0.5% potassium, ideal. So you have that nutrient, little bit that's available in the first 2-3 weeks. But then the biggest fraction that you want is organic nitrogen that will be a resource for the next 10 to 12 months or longer. So that's building soils. As you grow plants and as plants slough off the root system, they're always going to be passively building organic matter for you as long as you have a healthy biomass and you have a biomass to break that down. You have to have bacteria to break down an organic fertilizer, to break down organic nitrogen. I think we're probably all aware that no plant that we deal with anywhere around can process organic nitrogen. Organic nitrogen is found in grains and animal byproducts, leaves, any plant in nature, any organic material. Organic nitrogen, think of nitrogen as a building block for amino acid and protein. So when you have an organic fertilizer, the nitrogen is coming from the protein in the soy, the protein in the feather meal, whatever that nitrogen source is. Plants can't use it. They can't do anything with it. If you don't have an active bacterial population, you wasted your money on the fertilizer because it's just going to sit there. It's going to convert out to nitrate. It's going to leach, and it's going to be a pollutant. So you have to have, so that's the steps. Organic nitrogen, broken down by microbes, converted to the inorganic form of ammonium first. So the bacteria get that nitrogen in their bodies because they've worked at it. They're a high nitrogen organism. I'll show you that in a minute. Protozoans eat the bacteria, release that nitrogen as ammonium, goes on to the exchange site. Some goes directly to the plant. Nitrifiers come in. Leighton talked about that. He'll talk about it more. Convert ammonium, and now the plant gets exactly what it needs. Soil organic matter fraction drives all of that. It can increase water holding capacity. So if we're looking to reduce irrigation or looking to make a plant more stable in a non-irrigated situation, exchange capacity improves, feeds the microbes, buffers the pH, improves structure. We'll talk about that in the next couple slides. Increases productivity of soil. So if I said 3% organic matter is the low line for successful horticultural growth, as you move up to 4%, 5%, 6%, you're increasing the productivity of your soil. Now that doesn't mean you're going to skyrocket it indefinitely because there's a cap. And generally I think you want to keep in mind that in a field production situation that organic matter shouldn't probably exceed 10, 12%. Because then you're going to get a little bit of I think container production, totally different. So when we're designing container production, we can pull organic matter fractions up to 40% or higher. So that is very different when you're going in a container or outside. Soil structure, again, probably next to organic matter, the most important concept that I can give you. And this is the arrangement of the solid particles and the air pockets that surround them. So those pockets of air are referred to as pore space, P-O-R-E, pore space. It's the creation of pore space, and it's bacteria, it's the microbial population that creates soil structure. If you use synthetic fertilizers, you have all that salt, you decrease the microbial population and its activity, therefore you're degrading soil structure. As microbial populations go down and down and down, eventually you're going to end up with dust. You're going to end up with soil that just crumbles. You know, it's the glomalin, it's the excretions of the microbial population that are the glues that hold soil together so it looks like what it does when we pick up a handful of it. So it's about how they bind together and that arrangement that creates that pore space. And again, we come back to structure is influenced by texture, chemistry, and biological life. So there's the integration of all of that. This just shows different structures around the soil structures around North America, and how, you can have some of those, that are single grain soils where water moves rapidly through. And then you go all the way over to the right to a massive soil or a platy soil where water is extremely slow to move in. Platy means those clay plates sitting on top of each other. So again, knowing what is happening from the science perspective goes a long way to making good judgments on things. Go soil horizon. So Leighton showed you a slide on this. Just very, at the very general level, these are layers that are parallel. The structures and physical characteristics of any individual horizon are different from the ones above and the layers below. Most soils have at least 3 or 4 horizons. They're defined, obvious physical. If you were able to go into the backhoe and dig a pit and look, you could just, and I've had that opportunity to do that, and you get right down in there and you can look at those horizons and you measure the depth of the OAB horizons and how that goes, and that's what it looks like there. So the O is the organic layer of the detritus that's right on the very surface. The A horizon is where we're soil testing. Not to say that nutrients don't move into the B horizon, because they do, or not to say that microbes are only in the A, because part of what we're doing in field production when we move into organic and promote the active biological life is we want those microbes, and we know they will, move from the A horizon to the B horizon, and what they're doing there is improving the soil quality of the subsoil of the B horizon. And that's really part of the strategy, because most of the growth, most of everything that's going to happen is in the A horizon, but that's actually what does happen. Down below in the C, that's where all the pesticides and synthetic fertilizers and nitrate and all of the soluble nitrogen accumulates, is down in the substratum. And it moves. That's when it moves down there. It doesn't move from the A or B horizon and become a pollutant. It goes right down to the C horizon, and then either can get into groundwater or can travel horizontally and find its way. Water seeks its lowest point, and it's going to carry those, those unwanted compounds with them. So weathering of soil first occurs at the surface and then works its way down. Upper layers have been changed the most. The deeper layers are still similar to the parent rock material. So the big change in soil, and it's taken millions of years, to make that change. But we're in the O, A, and a little bit of the B horizon for our growth. Different soils can be productive, so we don't have to say that any one soil is the productive soil. We can have a sandy soil with high organic matter. We can have a loam soil, that's that balance of sand and clay, with medium organic matter, or you can have a clay soil with lower organic matter, and all 3 can be equally productive. The message is that we need to soil test to find out what we have, and then make our management strategies from that perspective. Soil chemistry, so this is a big one. Now we're moving into how that plant's actually getting the nutrients that it that it needs. So we have these nutrient pools, I guess is probably the best way to, that I've found to describe it. So in the middle you have soil solution. Now solution doesn't mean like it's a big, like putting some soil in a jar of water and mostly water. It's soil that has moisture to it. So just think of soil solution as soil that is moist. So we have the inorganic nutrient pool. These are things like phosphorus and potassium, calcium and magnesium that are found in nature and a natural part of soils that are water insoluble. So all of those are water insoluble mineral nutrients. They're there, they're not soluble, they have to be chelated or made soluble before the plant can use it. So you have that inorganic nutrient coming in. It actually is the microbial population, the humic acid fractions, the humic fraction. Those are the chelators, organic acids. If you're buying phosphorus in a conventional fertilizer and you put it down, that phosphorus is solubilized because we've heard of the words treble superphosphate. Those that are growers, that's a big amount of phosphorus. Well, all the phosphorus that's in conventional fertilizers is natural. It's softer black rock phosphate that has been reacted with hydrochloric or sulfuric acid before it goes into the bag. So the minute it comes in contact with soil moisture, it's available. So it's chelated before it goes in the bag. In a natural system, we're relying on excretion and organic acids from the biomass to act as the chelator. So that gets nutrient in there. We have the organic fraction over on the left side. So that is the organic matter fraction. That is the decomposition of organic particles, pieces, deceased organisms. Leaves that are broken down, compost if we put in there, that's the organic fraction, and that is converting that organic form of nitrogen to the inorganic so that root extraction, can pull it right out of the soil. Then we have the biological fraction. That's the bacteria breaking things down, the higher level predator consuming the bacteria and releasing the nitrogen in a plant available form. And then you have management inputs. So the way I manage is I take I know what I want to deliver to any individual crop I'm trying to grow. So I know what my target is. What do I want that plant to have available in its growth cycle? And what do I want to have available at what time in its growth cycle? So I simply take a credit. I look and say, what am I going to get from the inorganic fraction? How much am I going to get from the organic fraction? What am I going to get from the biological fraction? I add that all up and see how much that's going to give me. And then my management input only is there to make up the difference. The goal is to not have to go to the management input. The goal is to get all the other three to do the work for you so that you're not buying an input to go in there. So that's that sort of is that strategy is that and again, you need that soil test in the beginning to tell you, exactly what's going on. But once you do that and you are able to get a good, idea of what is being produced within the system, and that's how until you get these systems highly functioning, you probably will need some input, whether it's a compost tea, whether it is an incorporation of a compost, whether it is a little bit of soy nitrogen or a little feather meal to get the system up and running to the point when you can break the dependence upon that bag. So identification, this is where soil testing comes in. Total nutrients are not reported generally in soils. It's the exchangeable nutrients that are reported. When we soil test, we're looking at available nutrients, those that are soluble. So I guess my best message on soil testing, specifically for soil chemistry, is that when you choose a laboratory, you pick one and stick with it and don't bounce from lab to lab, and you understand that they take that bag of soil from you and they're going to put an acid in there to solubilize those nutrients, because the nutrients that you're in that soil largely are insoluble and they can't report them, they can't read it. When they do that extraction with the acid, there's either a weak acid or a strong acid solution. Weak acid is called modified Morgan. Strong acid is a malic 3 extraction. So malic 3 is solubilizing most of the nutrients that are in there and giving you a total projected number of what potentially could be available to the plant. Modified Morgan, which I prefer and a lot of people do, is a weak acid that does not solubilize all the nutrients, but it's more relative to what is happening in nature, what you can expect that plant to have tomorrow, not the potential that you could get out of the whole system. So and that's really what if we understand the potential, and what happens if I send a bag of soil out and one is a modified Morgan, I'm going to get a rating of, say, 25 to 30 parts per million phosphorus, and it's going to be high. If I do it in a malic 3 strong acid extraction, it's going to be 120 parts per million phosphorus, and that's going to be high. But the whole 120 parts per million phosphorus isn't available, but the 25 ppm is. So that's how we end up, looking at those things. Then carbon. Think of carbon as the fuel, the driver, the energy source for microbes. Microbes get processed nitrogen and phosphorus and all of those things, but carbon is their fuel. Humus is the driver of the system. So if we look at this, if you go into the A and B horizons, you look at the pools of organic carbon, and you go under tree, they're always higher in trees than in grasses, just because of the way trees go. So, there's different pools of N and P in the A and B horizons, so they're also greater under trees. Higher organic matter contributes to the higher level of nutrient. So as organic matter rises, nutrient rises, and carbon rises. So now we can notice that we have a similarity between the organic matter fraction pool and the nitrogen and phosphorus pools. And that's really what we're trying to do, is to build up these pools in the soil of N and P so that the soil can function. And we understand that we talk about phosphorus, but the plant can only use it as phosphate. When phosphorus combines with hydrogen and oxygen, forms phosphate, and that's the plant available soil. So all of this, you look under trees, you look in the rhizosphere, you look in the root zone, you follow these pools, and you come to the conclusion that the primary, source of these nutrients is from the organic matter fraction. So that's really what we're focusing on. So now we have a biological nutrient pool. So that big square in the middle, bacteria, fungi, protozoa, microarthropods. So you look at the bottom left, exchangeable nutrients easily pulled off of surfaces, easy to make soluble, dissolved in soil solution. Really tiny little square there, but look at the big square. Total of all pools, so without organisms to retain the soluble nutrients that a plant does not take up, or to exchange or to change this insoluble to soluble, there never will be any new soluble nutrients. So that's why you have to have the biological fraction active in a natural program. Soil conditions can affect it in the presence or absence of oxygen. Anaerobic, oxygen. Anaerobic, no oxygen. So if you just look at nitrogen as one example, and you could do this with phosphorus and sulfur and across the board, but in a well-oxygenated soil with good pore space, the dominant nitrogen form in soil organic matter is from the protein, and that is where the organisms are processing it. You also have the inorganic forms that are leachable and plant available, nitrate, nitrite, and then ammonium that's not attracted to the exchange sites. And we have an oxidation going on and a process that is continually evolving. Once you lose oxygen and go anaerobic, now all you have is organisms to make it available, and they're not the right ones that are going. They're the anaerobes. They're not functioning at the same level. And then that nitrate and ammonium that is critical to plant growth turns into ammonia, gases, nitrous oxide, that have no benefit to plant growth. Oxidation then is reduced. So what happens in low oxygen soils is any valuable nitrogen to the plant is converted to a meaningless gas. Ammonia is a gas, and it has no potential to influence positive growth. Anaerobic conditions, very interesting thing that we don't always focus on. Toxic materials are produced in an anaerobic soil. So once you lose oxygen, the microbes that are in there begin to take themselves into dormancy. They don't all outright die, but they protect themselves. They know that harsh conditions are here. There's no oxygen, there's too much water, compaction, whatever that may be, microbial activity is severely diminished. So then the good guys are not working. The bad guys take over. Very often they're the disease causers or the pathogens because they can thrive in an anaerobic soil. Alcohol is produced in anaerobic soils. 1 part per million alcohol can solubilize a plant cell wall. So in a very compacted soil, a waterlogged soil, it's not uncommon to have 20 parts per million alcohol. 20 ppm alcohol is simply going to dissolve that plant root. It's going to just start to go from the most tender root hairs right up and simply degrade that root. When I talk to turf managers, soccer fields, most of you have seen an athletic field, somewhere along the line, and you look at the goal in the soccer field, and there's always a big bare spot there, or the middle of a football field, there's a bare spot. No, it's not just the kids or the athletes that are tearing up that grass. It's that it's so compacted, there's no oxygen, alcohol is being produced and it's just solubilizing all the roots of that turf grass and killing it. And then the plant dies from the bottom up. So that's what's happening. You can reverse this by aeration. Now, Leighton made a really good point. The balance between too much aeration and not enough. If you aerate too much, same thing as a compost pile. You get too much oxygen, too many things going on there, you're not going to have a functional system. So it's all about balance. Everything is about balance. So if we need to loosen soils, if we need to introduce oxygen, we only do that after some type of a test, whether it's a penetrometer, whether it's a screwdriver test, whatever that may be, whether it's a biological test, and you go down there at the 8 or 10 inch root depth, and you do a biological sample and find out that you have anaerobes and not the good guys, then that is when you do that strategy. But you don't just, people will ruin a compost pile, but I got to turn it. Too much oxygen, and the whole thing just goes south. So it's the same thing in ag, any type of ag production. So again, it becomes that fine balance. Soil biological life. In a highly aerobic, healthy soil, healthy biological life, all of those statements are true. Nutrients are held in the soil. Water is retained in the soil. Disease doesn't have a functional place to grow. Eggs of many insect pests become a food source for biological life. Think about it. You have some of the soil-borne insects, when they lay their eggs, they just think of a beetle grub as an example. Lays the egg. When the egg gets laid, it's microscopic. If you have a healthy biological, community working there, that's going to get gobbled up as a food source before it ever gets to become a damaging pest. Nutrients are cycled at the correct rate that the plant needs, and the plant controls nutrient availability through exudate production. Functions: nutrient retention, water retention, nutrient cycling, building and maintaining structure, breakdown of toxins and pollutants, and disease suppression. Difference. So this is an interesting slide that a good friend of mine, his name is Paul Wagner, and he owns probably the best, in my mind, one of the best biological laboratories in the country back in New York, out on Long Island in New York. And he does by a long way, it's the same type of thing that Earth Fort does up in Oregon and Corvallis. But he's back on the East Coast, and he gave me this slide. On the left is soil. Organisms build soil structure. Nutrients are held onto in the soil. Water is retained. Water moves slowly through the soil. And at the end, down the bottom, we have clean water. On the right, no organisms, minimal structure. Water is not held in the pore spaces. Water moves rapidly through. Leaching, erosion, and runoff are the result. Water moves clay, silt, and inorganic chemicals. There's no cleaning process. You don't have the microbes now. You just have a pile of dirt. Yes?
What was his name in the lab again?
Paul Wagner, Soil Food Web, New York. So he does all my testing, even out from here in California. I send it all back to the East Coast. And he does the full biological testing of pretty much anything. Test compost teas, test compost, test soils from all over the country. Really, really great guy, and more than willing to help, anytime, answer questions, which a lot of the laboratories, soil chemistry and texture, they don't really want to talk to you too much. They just give you the test and give you the results. Paul's a really good guy. He likes to get into it and work with it. Nutrients in soil. So let's talk a little. Yes?
By that comparison, with then looking at people that now just grow cocoa or cocoa highlight, would you look at that as dirt? It's just washing through.
Yeah, that would actually fall onto that spectrum for sure. And you can grow in it. I mean, you can grow in 100% sand if you have to, but yeah, you have to know that that's what's happening. So you really get away from the classification of something as a soil. Yep. And it's the same thing. I mean, soil is at the front. When you look at the National Organic Program for Agriculture, right? This is one of my pet peeves, so I might, now that we mentioned that. But, the definition of organic is soil-based system. Biologically active soil-based system. So now, can anybody tell me in our world of organic food production how hydroponic can be certified organic? How can fish farming be certified organic? It's no soil. It doesn't fall in the definition of organic agriculture. So that's big business coming in and saying, we want to make some money and we want to sidestep things and want to grow in water and just put soluble nutrients in there, bypass the microbes, buy everything. No chemicals, but we're bypassing. So organic really by definition means soils and soil microbial organisms. Nutrients in soil. So soil is the major source of nutrients needed for the growth of plants. The three main macronutrients are nitrogen, phosphorus, and potassium. The second tier macronutrients are calcium, magnesium, and sulfur. So collectively, these are the 6 that are most important that are found in soils. We measure them. Like when I do projects, I test water that goes into the system. I test soil, and then I test plant tissue. And I look at what the nutrients are and how they're moving and how much actually gets up into plant tissue. Nutrition, by definition, the supply and absorption of specific chemical compounds, not synthetic chemicals, or organic chemical compounds needed for normal growth and metabolism of plants. Nutrients, chemical compounds that function as raw materials for the synthesis of different structural and functional substances of plant. Think of that word, raw materials, and that's exactly what they are. If you have a fertilizer bag, or what's happening in the soil, nitrogen, phosphorus, and potassium are not plant food. There's no food for any plant in a bag of fertilizer. There's no food for any plant in compost. All of that is a raw material. Think about it. Now you put N, P, and K. If you got nitrogen, nitrogen does certain things. We know it'll push growth. It'll push some root growth. It'll make a plant green up. You can green it up with nitrogen. That's chlorophyll, right? Chlorophyll is in the plant. That's the green in all of our leaves. It's on the underside of all foliage. All leaves are opening latent reverted stomata that open and close, typically dawn and dusk when the air is calm. So you have all the chlorophyll, the green, carbon dioxide up in the atmosphere. In the presence of the sun's energy and moisture, stomata open, carbon dioxide goes right inside of that leaf, reacts chemically with the chlorophyll. Carbohydrate, sugar, and amino acid are the resulting production. That's plant food. So the plant makes its own food. All of these macronutrients are just raw materials that act as catalysts in that physiological process. Mineral nutrients, that's those inorganic minerals. Think of the nutrient pools I showed about, the inorganic that are obtained from the soil, which are used as raw materials once they are chelated. Nutrition, the absorption, utilization, and assimilation of inorganic compounds or minerals, plants, synthesis of essential material needed for growth, development, structure, and physiology. So it's not food. None of these NPK, Cal, Mag, and sulfur are all raw materials that work in individual physiological processes. Mineral nutritional elements are available to the plant as the ion or the anion, cation absorbed through the root. They can occur in the aqueous portion of the soil. Adsorbed. Adsorbed means attracted to those exchange sites. They're on the CEC sites. They can be insoluble inorganic compounds, or they can be constituents of organic compounds. So they're either residues of plants, animals, or living organisms. That is the organic fraction of nitrogen. And it's there, it exists there, but nothing's going to happen to it unless you have active biomass to make that happen. So we have macronutrients. This is all based on concentrations that are found in plants. They're present in plant tissue. So we have carbon, hydrogen, oxygen, NPK, Cal, Mag, and sulfur. Nitrogen, phosphorus, and potassium are obtained from the soil. Cal, Mag, and sulfur also obtained from the soil, needed in lesser quality. Oxygen and hydrogen obtained from the air. Carbon can be either soil or air. Then we have the micronutrients, needed in a much smaller amount by most plants, also referred to as trace elements or trace minerals. They generally include iron, manganese, copper, molybdenum, zinc, and chlorine. So very small. We test for that in soils. I test for that in tissue. So again, looking at micronutrient, and it's not uncommon to have, micronutrient deficiencies in soils. And depending upon the plant that we're trying to grow, and one of the things now working with, Leighton and I talk all the time about this, and we're working to sort of collaboratively create a database for the cannabis plant and say, where do we want micronutrient levels to be with all of this, and what's our range, and where do we know, when do we need to amend, and when can we get by with a lower one, and trying to get that in a shareable, form where we can simplify, what happens. So let's look at nitrogen. It can exist in the soil in the organic form, as ammonium, as nitrite, and as nitrate. Can't be used by the plant in number 1. It can in number 2, 3, or 4. Very little as nitrite, because it passes from ammonium to nitrite and then pretty quickly out to nitrate. It can be used in the nitrate form, but we generally don't acknowledge that much of it because not too much happens there. Required by all parts of the plant, particularly the meristematic tissue, that's the growth. So nitrogen drives initial growth in the cannabis plant because we're pushing meristematic tissue, the growth tip of the plant. That's that the meristem, all growth, originates from that. Primary constituents are proteins, nucleic acids, vitamins, hormones, rapid growth, leaf size increase, hastens crop maturity, promotes fruit and seed development, but then phosphorus kicks in and really establishes that. So think of nitrogen as responsible for the vegetative growth in plants, and phosphorus for the reproductive, because every plant is going to switch, and we all know how we could, we can manipulate day length, we can make things happen, we can grow plants 20 feet tall, or we can have them, here, and we can flower it out by day length. Phosphorus kicks in the second half of the cycle. Bud development, bud size, flower size, all of that is phosphorus is governing that, and nitrogen is governing the beginning part of that growth cycle. It's absorbed by plants from the soil in the form of phosphate, H2PO4, called orthophosphate. The only way the plant can absorb that when it is combined with hydrogen and oxygen. It cannot be taken in as elemental phosphorus. Easily redistributed in most plants from one organ to another, lost from the older leaves, accumulates in the younger leaves, developing flowers and seeds. Constituent of cellular membranes, proteins, nucleic acid, energy transfer. If photosynthesis is the process that makes plant energy, carbohydrate is energy, respiration is the opposite. That's taking that produced energy and turning it into growth. Phosphorus is critical in that aspect of it. Activates amino acid production. Used in protein synthesis, central to photosynthesis and respiration. So that's really way down on what phosphorus does. Potassium can be absorbed in the elemental form as K+. Required in larger quantities, meristematic tissue, buds, leaves, and root tips. Determines cation-anion balance, activates enzymes, opening and closing of stomata, maintains turgidity, strength of cellular tissue, facilitates cell division and growth, and the bottom, central to disease resistance. So if you're looking to build stress resistance in the cannabis plant, to stand up to stresses, you want potassium levels. If I'm doing a soil test, I want potassium to be right up at the top. I'm not happy with it in the medium range. I want it to be optimum. Not excessive. I mean, nothing should be at excess. But if I have potassium, no matter what kind of plant I'm growing, at the optimum range, I'm bringing all those desirable characteristics of stress resistance into play. Calcium can be directly absorbed as a calcium ion. It can be held on to, adsorbed, again, exchange sites. Stability of soil particles. So calcium is central to maintaining good soil structure. So now think of calcium as that second tier macronutrient that is responsible for, we saw that calcium, the exudate coming out of the root, going on to the exchange site, central to the growth of the plant, central to the health of the microbial community, and now stability of maintaining soil particles. So calcium is pretty important. So again, soil test, want to find out where that is. Meristematic tissue, mobile, not translocatable. And it's easily leached. It can be easily moved through soils. That's why we want to make sure with the soil test that we have enough room on the exchange sites to hold on to it. If you don't have enough room on the exchange sites, then we're not going to hold on to it in the soil. All of these, steps are involved with calcium: cell elongation, division, germination, pollen growth, activation of enzymes. So it is even though it's a second-tier macronutrient, pretty important. Magnesium, again, on the exchange sites, fruit and nut formation, essential for the germination of seeds. Moves from the aging leaves to developing seeds during the life cycle of a plant. Structural component of the chlorophyll molecule. So a little more subtle things that are happening here, but if we want good chlorophyll density to undergo photosynthesis at maximum, then magnesium is central to that. Sulfur from the soil, primary source available to the plant, can be taken up by the leaves in the gaseous form through the stomata, largely found in stems and root tips of young leaves. It can be reactivated during senescence. Senescence is the aging process. So the sulfur kicks back in at the end of the cycle from maturity to death of plant tissue. Again, it comes back to being this sort of subtle component of amino acid, protein, and vitamin, essential to produce chlorophyll. So again, soil testing to find out where these things are, and it really is about balance and making sure that we're getting off on the right start. Two major types of soil carbon, from the biomass and the non-biomass. Carbon is the energy in the soil. So the biomass is living bacteria and fungi, and the non-biomass is cellulose, starch, and the lignin of dead plants. So typically, when we're testing carbon, we see the three letters TOC, total organic carbon. So that's the carbon stored in soil organic matter. And again, coming back to organic matter, that is holding carbon in the form of humus. Enters the soil through the decomposition of plant and animal residues, root exudates, living and dead microorganisms, and soil biota. So think of this, we just talked about photosynthesis. Carbon dioxide up here, chlorophyll going in, CO2 reacting with chlorophyll to form carbohydrate. 80% of that carbohydrate that is produced during the process of photosynthesis goes down in the root system. Only 20% of it stays to drive the upper portion of the plant. Of that 80% that goes into the root system, 40% of that, or half of that, becomes an exudate that goes right out through the root into the soil. Cake and ice cream for the microbes, energy source for the microbes. So desirable microbes are colonizing the root of the plant to make use of that carbohydrate exudate. So now you think of the value of a plant when all of the global warming and things we're dealing with and trying to reduce CO2 emissions. But what if we have a healthy, organically grown plant that's firing on all cylinders and everything is operating efficiently? Think of how much more carbon dioxide we're scrubbing out of here and sequestering as carbon down there. And that's how we look at it, that our plant is producing a very valuable function by actually scrubbing the atmosphere and cleaning. And that happens more efficiently when you're growing in a healthy organic system. Again, soil organic matter, just in here, just to mention that most analytical methods don't distinguish between decomposed and non-decomposed residues, right? So when you do a soil test, the test for soil organic matter is called LOI, loss on ignition. They weigh the sample, they burn the sample, and then they weigh it. All the organic material burns off, and all that's left is the mineral sand, silt, and clay. So organic matter is a representation by weight of soil. So 5% organic matter means 5% of that soil weight was the organic fraction. So when I do a soil test, I want to clean my roots. Leighton talked about doing a test for, having Efren do a test for mycorrhizal, and he wants the root. You have to have the root. You can't do a mycorrhizal without the root. In this case, you don't want the root because the root is undecomposed organic material. So they're going to burn it. So pieces of the root or parts of the plant or wood chips or whatever it may be in and around there, if that is in that sample, that's going to get burned off, and that's going to give you an untrue representation of that weight. So when we do this soil chemistry test, we want to clean it. We just want soil. And so then we know that when we're burning off that through the ignition process, you're burning off decomposed, as opposed to undecomposed organic particles. Let's see, we've done that. This shows you soil organic matter, 58% carbon, more or less. So again, you can see how I keep weaving through here, and we keep coming back to organic matter. And that organic matter fraction, I can't stress enough how, how important that is. That soil organic carbon probably is one of the more important constituents of soil because it has the ability, the distinct ability to, support and produce or to affect plant growth, I guess is the best word, and drive the microbial population at the same time. Sugars bind mineral particles together into microaggregates. Glomalin, soil organic matter substance that makes up 20% of soil carbon. That is the glue that the aggregates binds them together, stabilizes structure, gives soil the ability to be resistant to erosion, but porous enough to allow water, air, and plant roots to move through. And that's the balance. That's the balance between aeration and non-aeration, loosening soil or not loosening soil. And if we have an ample supply of carbon within the organic matter fraction, that's doing a lot of the work for us. One of the things that we know, and it's true in cannabis production, container production, field production, it's true in those soccer fields, baseball fields that I manage, is that the more we can improve the biological life within the organic matter fraction, the easier it is to keep oxygen and pore space there. You don't have to aerate as often. You don't have to loosen soil as often because the microbes are going to do that for you. I think you all probably understand that concept a lot better than some of these turf managers that I would say, well, if you improve the biology under this soccer field, you're not going to have to aerate as many times a year. They don't get that concept because it's hard for them to understand that microbes are loosening soils just through their activity. So as growers, you guys are in a whole different class of being able to understand that concept where, somebody that's out there managing some of these other types of landscapes, that's probably one of my most difficult concepts to get across to them, is that if you spend some time building and growing and supporting and feeding the biomass, all of your cultural things that follow after are going to be easier for you. Humus, one of the most important things that we can talk about. It participates in aggregate stability, nutrient retention, CEC, water holding. Humification is the process that breaks down the organic matter fraction. The best simple definition of humus is the end product of decomposition. When any organic material or particle can be decomposed no further, it becomes humus, and humus can be a long-term stable resource in the soil 50 or 100 years because it is then resistant to breakdown. So you have to have chemically stable humus. That's really important. It has the ability to suppress disease. At the end product of decomposition, the reason it lasts is because it's not further decomposed by carbon dioxide. It's protected from carbon dioxide. Microbial enzyme action because it's hidden inside of small aggregates. So humus can be a long carbon chain, and there's all these nooks and crannies in there, and it's all tucked in there, and it's protected from further decomposition by from carbon dioxide because it attaches tightly to the clay particles. So in those heavy clay soils, that you have, there's drawbacks and there's issues, but there's also distinct advantages that you have that people that grow in high sandy soils don't have the ability to take advantage of that. If humus is not protected in that way from CO2, it'll be broken down and decomposed and lost within 10 years, called labile as opposed to stable. And that's a situation that you don't want. Stable humus contributes directly to the pool of plant available nutrients, doesn't contribute a lot to that, but it does play a significant part in maintaining physical soil structure and support of the biomass. And that's really what's all these little things, all these little nuances that end up supporting the biomass. So when you go back to my first slides there of the 3 circles that showed no relation between texture, chemistry, and biology, and then I brought those circles all together and said humus is central to that. This is why. That's what ties that all together. So as soil organic matter increases, carbon increases. Greater biological diversity in the soil. Greater diversity leads to increasing biological control of plant disease and pests. So if we're in an organic system now, we do have organic pesticides that are allowed in production. They can be US EPA 25B exempt or OMRI certified, Organic Materials Review Institute certified. But the goal, and I don't include, even though those are allowed and they're at my discretion to be able to use in a project, I don't ever schedule them into the beginning of the process, only as a rescue treatment needed, even organic. If it's an organic product, it's only a last ditch resort because my first emphasis is going to be on this and to try to make that happen internally without added input. And you start to buy some of these biological, I get to the luxury of going to the US EPA in Washington every couple of years and sitting down with the regulators and talking. And the biggest movement now in pesticide is the biorational, Office of Biorational, where you have one organism that can outcompete another one. But it's always a trip when you sit and talk to the EPA and you listen to what they say. And, all of these pesticide laws and everything, it's just a little side note though, but EPA, is risk assessment. When they look at pesticides, it's all about risk assessment. Does it hurt you or doesn't it? If risk outweighs the benefit, it doesn't come to market. If benefit of the pesticide, organic or synthetic, outweighs the risk, they'll bring it to market. When I was at the EPA 2 years ago, at the OPP, Office of Pesticide Programs, those are the guys up here that are making the decision. They actually said to us that they believe that they have an obligation to provide financial benefit to the registrant. They have an obligation to provide a benefit to the registrant that can outweigh the protection or the safety of us. So the ability of corporate America to make a profit factors in their decision-making process. Right out of their mouth. And I think the minute that came out of his mouth, he regretted every minute of it because somebody called him on it. But that's the underlying thinking in there. That's really what, this whole thing is up against. A little bit. We're just going to blast through a little bit of soil biology, and then I'm going to leave the real technical stuff to Leighton, because he's the man. He's the guy that's got this all figured out and gonna lead us. You guys, I can't tell you how lucky you are to be able to spend 2 or 3 days with this guy, because he's on the cutting edge of all of this. And I don't think there's any research scientist in the country at any of the institutions of higher learning that have uncovered and thinking the way he's thinking and really drilling into all this, because there's a big difference in having somebody come talk here that's an academic as opposed to somebody that's out there doing it and figuring out what works. There's such a big difference. And I'm not an academic. I'm the furthest thing from an academic you ever would see. But it's all about experience and what works. And he's got it. So this is just going to be a real high-level overview. What is it? How do we best support it? So collectively, it has been coined as the soil food web. is developed a number of years ago by a colleague of ours, Elaine Ingham, and sort of branded it and put this name on it. Not branded it, but attached this name to it. So it's a term that was coined. Different species of soil microorganisms participate in active ways, creation and maintaining structure, growth, nutrition, disease resistant, nutrient availability, sustained by the organic matter fraction. Natural organic system does not rely on synthetic input for nutrition. Pest control, focus on creation and maintaining of that good environment. Understanding the biomass includes understanding the function of both the active and passive organisms. So there's guys down there that are passive and just waiting to be woken up and work for us. And there's guys down there that are working and sort of doing their thing. So, you may have heard the term biostimulant. Biostimulant just means something that's going to go in there that's going to positively affect that community down there to get it to work in a more efficient way for us. So our focus is to make as much of that total number active and working. And, as it becomes active, we can do that. And a lot of it depends on what we want to do. Our intensity of management. Cultural intensity is everything that you put in to grow your crop. The amount of labor, water, inputs if you have to buy it, education, continuing education. All of that is cultural intensity that gets you to a spot. Everything that's going into growing that plant to get the results to meet those expectations that you're after. So, these are the guys, once again, a couple of repetitive slides here. My best understanding, as I mentioned, of the highest managed landscape or growing any crop I can grow is to mimic what's happening in nature. So I'm not going to impose man-made strategies on the cannabis plant. I'm going to look at how that works in a natural system with nature and do everything I can to enhance that. So this is just a slide on systems-based management. You address the system above ground, below ground, relationship between the plant and the soil. We can't ever forget that. Soil gives the plant the compounds that it needs, and the plant returns exudates back to the soil. So it's a give and a take. It's a give and a take. It's a secular system that we're working in. And that's what's wrong with conventional agriculture, because for decades and decades in the Midwest, in the heartland, they've just been pulling from the soil, taking. And now you've got places out there that the soil's not going to recover for a couple hundred years, because all that has happened is just pulling out of the soil and never creating and giving back. So there's the slide. You can shoot that one, but that's the one that 80% that goes down there. This is the carbohydrate storage in the soil, sequestering carbon in the soil, and this is the science behind how that is happening. Just a couple on mycorrhizal. Leighton touched on that, and he'll talk more about that. But this is that association where the reproductive strands, the hyphae, attach themselves. They either grow into the root of a plant or attach themselves to the outside of a root, and they're mining the soil. I think the next slide. No, yeah, that's the one I want. So so mycorrhizal, so I won't go into this. You got ecto and endo, ecto trees, Leighton is talking about, and he'll talk to you more specifically about strains of mycorrhizae that will colonize rapidly a cannabis plant, or not rapidly, let's say, have the ability to colonize within the life cycle production of the plant. But here we have one, and notice there we have those root hairs left and right on that root. And they are mining that soil for nutrient. That's also now referred to as a depletion zone, because that root has mined all the nutrient in its immediate area, right where it's pulling from, and it's pulled all the nutrient. There's going to be no further nutrient there available until microbes move in to break down more organic matter, or we go to a bag of something and put it down there and add nutrient. If we inoculate with mycorrhiza, then what's going to happen is, you can see on the right that their reproductive strands are going to go many meters beyond the root of that plant, and they're going to continually mine the soil for not just nitrogen and phosphorus, but as Leighton said, we're finding and so much more that we don't know, and we're finding all this out that they can do for us. And, these guys are going to work best when you're not putting a lot of fertilizer or nitrogen or inputs down there, because it's pretty well documented that if you introduce or you have mycorrhiza there and present and forming this association, and you continually jack the system up on nitrogen input, these organisms are going to just sit there and say, well, why do I have to work? Somebody's doing all the work for me. I'm just going to sit back and not do much of anything, and that's really what happens. So the introduction of this organism or the growth of this organism, and in some cases is a pretty good natural inoculum, and again, we test for that. We look at everyone can do that colonization test for you. But the idea that if you decide that this is a route that we want to go to work within the natural system, fertilizer, nitrogen has to be dropped way down, because you have to have the confidence that the system is going to do this. Now, that being said, if we're just starting off, or if we're new to getting into this, or if we're in a situation of converting from a more conventional management system to an organic system, there may be some need to have a reliance on a fertilizer bag until all this gets into place. Because it doesn't happen overnight, and it doesn't happen immediately, and it's not just saying, I'm doing this now, and I want to do this in the future, and in a space of a couple months, I'm going to make that all happen. So it's all a process, but it's also having the confidence on the stuff that Leighton's going to talk to you about, that it works, and that it's going to do that, and it's going to function in that way. And if you just stay the course, and my hardest thing is I get these systems put in place, and then somebody that I'm working with, and they may be 2,000 miles away, so I'm not right there, and they think, oh, well, I'm not happy, it's not going fast enough, and then they reach for a synthetic bag and dump it in there, and then everything gets set backwards. So as you embark on this path, and as you begin to embrace this, you just have to have the confidence that it's going to work. The plant's going to get better, production's going to be better, yield is going to be higher, the quality of that yield is going to improve, as you continually just have the confidence to move in that direction. Leighton talked about these. These are the saprophytes. These are the decomposers. Down the bottom, 1 gram of a non-rhizosphere, non-root zone forest soil, 600 million bacteria and meters of hyphae. In 1 gram in the root zone of a forest soil, look how it jumps to 10 billion and miles. So that really is, what's happening, the breakdown that's happening with association of root and plant. So bacteria and fungi decompose organic, retain nutrients, rebuild structures, suppress disease, produce exudates, feed bacteria and fungi, supported by the organic matter fraction. So a little bit repetitive here, but these are the lowest trophic. Then these are the predators. These are the protozoa feed on bacteria. Nematodes feed on fungi. They do a whole lot more than that. This really is high level here, but that's what is happening. Think of it as a predatory relationship there. They're competing for a chance to survive, and one organism is preying on another. The end result is nutrients being released in a plant available form. We have nematodes that have a relationship with fungi, and they do the same sort of thing that bacteria and protozoa do. Microarthropods, microscopic spiders, we'll say, make nutrients available, stimulate prey, build structure, and that Paul Wagner, the guy I mentioned, he refers to them as nature's taxi cabs, because a single-cell bacteria can hop on one of these guys. It helps disperse and distribute the biomass. So here is the science of the organisms. Bacteria, high nitrogen. Protozoa, low nitrogen. Protozoa consumes the bacteria, doesn't need any of that nitrogen, and that's why it can immediately slough it off and make it plant available, because it is not using any of the nitrogen that it consumes from the bacteria for its own survival, because it just doesn't need it. Same relationship between nematodes and fungi. These organisms, when the system is functioning properly, between active and total, these organisms can hold on to 15 pounds of nitrogen, 1,000 square feet a season in a healthy soil. Or they can cycle 2.5 pounds of nitrogen every 30 days to the root of the plant. So think about that. That's more nitrogen than you would even buy in a fertilizer bag. And so a lot of that's going to be held onto the exchange sites. That's nutrient in reserve. So that's what the system is doing. If you have the confidence to stay the course with what's happening there, then you stick the mycorrhiza on top of that and you mine further than the root can reach. That's the kind of nutrient that can be produced in a relatively short time. Anaerobic soil, I just only repeated this because fungi, the beneficial fungi that are the disease suppressors, in other words, the good guys outcompete the bad guys, we never should be reaching for a fungicide in any production ever again because we can make it happen naturally, but they cannot tolerate anaerobic soils. They're the first guys to go south when oxygen is lost in the soil. Now we know what plant and what organism colonization we want. So look at conifer trees and that very strongly fungal soil. And take a minute to read down the list and look what happens down in the bottom of the list when you're a very strongly bacterial soil. You're going to grow a weed population or an undesirable plant population. I gave a talk yesterday down in Sonoma, and it was to city turf managers and park people, and we talked about this and how the fungal to bacterial ratio, and that if I have a soil that's strongly bacterial and you got a soccer field that you don't want any weeds in there, we get trouble. So the first thing I'm going to do is to get a humate, a granular. I told I'm not even going to reach for nitrogen on your soccer field. I'm going to put a humate, carbon in there to get the fungal to bacterial ratio so that I don't have a microbial population in that soil that just wants to grow me weeds. So if I want weeds to go away, it's an organic system, so there's no herbicides being used, but it's getting the biomass in the right range for that plant. So, that comment down there, if you have a tree that wants that strong fungal dominance and it's growing in a bacterial dominant soil, what's going to happen? It's not going to be happy. It's going to get insects. There's going to be problems. Down in Irvine, I managed 32 shopping centers for a big company down there and switched all the nutrition from synthetic to organic. And I was dealing with bacterial soil, so bacterial that those palm trees and all the olive trees and the eucalyptus and everything that was growing down there wasn't happy because the soil was so contrary to what that plant wanted. So what would you think so think of that. So here I got a very urban environment, and it's a shopping center, but it's planted out like a botanical garden because they do that kind of thing down there. It's all for show. So if I had that situation with a strong bacterial dominance in the soil, and I had trees that wanted a fungal dominance, and I was on a liquid injector system injecting nutrients, but if I had to think out of the box, how do you think I very quickly tried to change that? Just threw some compost, got a fungal dominant compost, and top dressed under their bark mulch. So I made them scrape off, and they weren't happy about that. 6 million square feet of bed area, and all the high profile trees pulled all the bark mulch off, because that's not doing anything. That's just degrading soils. Leighton talked about that, virgin wood sucking nitrogen out, and put an inch of compost under all those trees, and then just simply put the bark mulch back on top of it, and tried to change the fungal dominant as fast as I could. So my last slide. How do we diagnose? We diagnose with soil tests. If we're looking for compaction, we're diagnosing with a penetrometer or a soil probe. We're trying to monitor root depth. Buying a soil probe would be a great thing to have, because you'd go down and you can actually track the root depth, that goes down there. We look at the root, soil smell, one of the first things I ever do. And people that, I'm a real hands-on type of person. When I'm doing a compost or a soil, the first thing I do is pick up a hand, I smell it. To me, you can smell, Leighton will tell you this, you can smell biological life. And you can smell the absence of biological life. So something simple as that, before it even goes to a laboratory, I'm going to pick it up, I'm going to smell it, I'm going to feel it. So we diagnose, so then my management strategies, we diagnose the soil conditions, we create the correct environment, we inoculate with needed organisms as might be necessary, and then we just simply make sure we provide those food resources to maintain a healthy biological environment. Now that can be, compost teas and things like that. That also fits into maintaining and that type of a strategy. So that's really what it all boils down to. Diagnosing, understanding what it is that we're growing in, what characteristics that has, and then how to manage that so that we break a dependence upon supplemental inputs and allow that system to function as best we can. So I think we probably have a few minutes if there's any questions, and then it probably is time to break, or I'll go here, 1, 2, 3.
What's the quickest way to increase the soil organic matter? Would it be through cover cropping or deep mulch, or what's your quickest way in experience?
Yeah, what's the quickest way to improve or increase the organic matter fraction? And it would be, one of the things that's going to happen on the more passive side is the sloughing off and the breaking down of the root system. Introducing well-aged compost and working that in and letting that work down. Those are probably the two immediate ways to do it. Cover cropping, if we don't have a plant there, and cover cropping with a legume that's going to fix nitrogen and then all at the same time then get turned in and be broken down to increase the organic matter fraction. Well-aged compost. That means one where biological activity drops at levels of 10% or less. So in composting, it's a heat process. It's the first stage in composting is mesophilic, thermophilic, second mesophilic, and maturity. Heat rises, heat declines. Different organisms do their work, and then here certain organisms, the mesophiles start, then the thermophiles, the high heat takes over. Second mesophiles return in the cooling down process, and then at maturity. Maturity is determined by stable carbon to nitrogen ratio. When we compost, we want to make sure that we have a 20-to-1 to 30-to-1 carbon to nitrogen ratio of the input going into it. And when it's all said and done and finished a year later, we want that to stabilize down to between 12-to-1 and 20-to-1. So 12-to-1 to 20-to-1 C to N ratio combined with a biological test that said activity is at 10% or less, that's well-aged, mature compost. Yes?
What is the best way to wildcraft humus to reinvigorate tired or out-of-balance containers?
So what is the best way to wildcraft humus? Leighton, I'm going to defer that one to you. Any thoughts on wildcrafting, humus, which we starting to that. I'm going to actually be doing that over in Maui next couple weeks. But what are your thoughts doing that locally here?
Silt is going to be your best thing. Silt kind of broken down to a very, very small particulate. It's mineable at creek edges, better yet, old swamps. But once you start playing with silt, you got to aerobically stabilize it. Otherwise, you're going to introduce the anaerobe. So how do you aerobically stabilize it? That would be taking it out, spreading it out, letting it dry, adding it to a compost tea brewer, something like that to build a dissolved, not because you're not going to kill all the anaerobes. But you have silt everywhere, and silt is probably the closest to cremate you can get without mining. I hope that answers.
Thanks.
One more question over here.
When you take soil sample tests per acre, how many do you recommend, or is that based off of like the percentage grade of the farm
Yep.
or location?
So how do you, when you take soil samples, what do you do or how much you do per acre? So what you want, the most important thing is you want random sampling. You want to go down, you pick a depth and you go down there. You want to, remember, you're sampling out of that A horizon. So, nutrients are going to get low. So you're going to take a little bit right up in the immediate rhizosphere where the plants are going to first take off and get established. And then you want to go down deeper where you know that root is going to be in the next 4, 5, 6 weeks. So if I were doing an acre, I would go and I would probably, randomly go through that acre and maybe take 12 to 15, maybe 20 individual samples. I'm going to mix them all together in a clean container, and then I'm going to form one composite sample. And that would, unless we have different things happening on that acre. So if you have a soil that exhibits certain characteristics in 1/2 acre, and then all of a sudden you move to another 1/2 acre and you get a visual difference happening, I'm going to stop and I'm going to make 2 samples. I saw, yes.
So say something along the lines of a 200-gallon smart pot. That's what we run is
A 200 what?
200-gallon smart pot, and we run about 70 of them with different cultivars inside of them. How would you go about doing the different testings for that, or the different plants uptaking the different amounts?
So plants taking up different amounts would be running with that. You'd do that with tissue analysis. So that would be, one of those measures with tissue. Because roots would probably be interchangeable and they're moving through there, I would be comfortable doing, a random sample through all aspects of, or through all areas of there, but I would fine tune it, with tissue, to make sure of the different cultivars. Now, does anybody here, and I was it you too, anybody doing a BRICS test, B-R-I-X test on cannabis production? That's great, that's cool. BRICS is a measure of sugars in plant tissue, which is also a measure of nutrition and quality and all of that. 10 years ago, people would, I can remember people saying organically grown produce is harmful and it's toxic because the plant's producing its own natural defenses to keep weeds out, and that's bad for people and all this. Well, time after time after time now, when you do BRICS for organic food production versus conventional, that retained sugars and the BRICS scores are always higher. So tissue analysis combined with BRICS, and BRICS, all you need is a refractometer, about $20 little piece of thing. It's light refraction. The higher the density of sugar, the different angle of incidence and refraction.
What I noticed from this brick, when I had plants that had pathogens or insects, it seemed like the cause of it was the brick level was low.
You're right, spot on. And so what I do now is I'm doing that out in the urban landscape, because that is exactly what it's about. We all know that insects attack the weak link out there in nature. Fungal diseases are opportunistic. They won't attack a healthy plant because the plant has the defenses, what we talked about. So as sugar density increases, simply if you have a sucking or a chewing insect that, starts to become a pest of a plant, it's because the sugar doesn't have the density. When you have high density sugars and high BRICS scores, that insect, attaches in there and tries to suck that out. It can't process it. It can't process that density of material that it's pulling out, and the insect just says, the heck with this, and goes find some other place to get it. And that's exactly what happens. And you monitor that with bricks. And bricks, you simply going out there with a mortar and pestle and grinding it all up and getting a little bit of all you need is 2 drops. You put it right on there, watch the light go through, and so you, through the period and life cycle of the crop, you monitor sugars in the cycle. Yes? The most right where? I had one that actually shocked me, and my number of protozoans combined was like 8 million. And that typically, you're not at that levels. I think one of them, it might have been flagellates, was up around 10 maybe. And so we had, that soil was producing 300 plus pounds of nitrogen per acre over a 90-day period. So that's how we measure that. The protozoa to active bacteria, and over 90 days, what can that do for me? And it was well over 300 pounds. And that's more than any of us would ever dream of putting. And but you'd go broke if you tried to buy that from a bag. But that was just all happening all by itself. Yeah, that was in the where was that? That was in Ohio. Yes.
Soil moisture levels and how that plays into the microbial health of the soil. Have you found what ideal moisture levels to foster growth better than others?
So ideal moisture level, that comes back to that field capacity. So for me, the most active I would think would be just below field capacity. When you have field capacity and then you dry it out just a little bit more and then you have a little bit more air pockets, it's all about air, oxygen as the stimulus for that happening. And as soils, and at some point they get too dry, and then they slow down in their activity because they're wanting more moisture. So my experience is just a tad below field capacity gives me.
That measurement, whether you're taking a percentage or millibars or it's going to differ based on the structure of the soil.
Absolutely. So that's why, like a lot of things that I say, you can't take it for gospel everywhere because it's so regionally affected by soils themselves. And with that slide I showed you with all the different blocky and platy and moving through soils, that has so much to do with it also. Yep.
Any comments on silica as a nutrient or reports to the plant or the soil?
That's sort of both ways. I haven't used it as a supplemental nutrient, but some people feel strongly that it is beneficial and has that, and I tend to agree with that. I have others that won't touch anything with silica and just will not introduce it into a system. So again, there's so many things that, it's basically individually what works for any one of us and trying it like that. So there is a lot of, another thing that I'm very strongly, I feel very strongly about is that what we're talking about here is really a lot site specific and up to each one of us on how we interpret our own growing space as opposed to cookie cutter. So it would be a total disservice for me to stand up and say everybody here has to do it this way or everybody has to do it that way or everybody in California do it this way and if I'm in Colorado you do it that way and I'm in Massachusetts you do it that way. But it really is, and I approach the same thing when I'm doing a public park. I'm site specific as opposed to cookie cutter. So, there's a lot of knowledge with all of you in the room, and I'm not professing to stand here and say that I've got all this knowledge. You guys collectively have way, as much or more than I do. So that's, and that's really what it's all about, is drawing on everybody's own individual knowledge and how that relates to what is happening in that site-specific situation, using a lot of these scientific principles and guidelines, to sort of guide decision-making strategies, but never intended to supersede the value and the importance of the site-specific nature of the plant manager. Yes?
Going back to the bricks thing, do you have any recommendations to increase brick levels on plants?
Just getting rid of synthetics and beginning to grow organically. And synthetics degrade bricks, they degrade all of that part of the system. So it really is just about beginning to embrace the organic system and knowing that once you reduce all of this, and then again, even organic fertilizers, reducing input and going to try to get that soil that's going to produce that 300 pounds of nitrogen on its own over a 90-day period. All of that is what's going to lead to the increased contribution of sugars to raise brick scores. Way up in the back. What, last question? Yep. Yeah, so that is a long question, and I think most of you probably heard that. And that's the perfect segue to sort of the table that I've just set here and where this is going to go today and tomorrow. And that's why, again, you got Leighton here. He's the microscope guy. He's working on exactly that. That's really his work. That's what he's focusing on, is taking all of those things, putting it under a microscope, and looking at how information can be communicated to you all, because it's not going to happen from a university. It's not going to happen from established institutional learning. It's going to happen from work like that that's happening. And that's exactly what he's working on, is how do we look and know what is the number that I'm looking for? What is the relationship of activity? What numbers are going to work best with this plant to produce that expectation? So that's where the advanced learning is going to come this afternoon and tomorrow, and take it to that level. And in all respects to Leighton, I don't think he has all the answers right now, but if you knew the level that he was working on this, and the energy and sort of the passion that he's putting into it, and I would say in the not too distant future, you all are going to have that kind of a resource that said, this is what I'm shooting for. Thank you very much. Appreciate it.